Right, let's see here. Make sure that's. Am I getting audio? Yeah. All right, 10 April. There you go. I'll pass that around. Find your way to chapter 26. Okay, what about homework? Any homework questions?
No.
Anybody got any to turn in? All right. They how's the exam coming? We're working on 23, right?
Yes.
Say again? Special, you said special relativity?
Yeah.
Why is it called special relativity? Special relativity, you look just at the effect of time and how speed affected our perceptions and how speed affected the way the universe works. It was all derived from the basic observation that the speed of light didn't change. It was the same in no matter what frame of reference you measure it in, regardless of how fast the source was moving, regardless how fast the receiver was moving, it made no difference. The speed of light was constant, was invariant. And of course, once he started examining, okay, well, and understand that at the time this was a problem. People were still arguing over whether or not there was such a thing as ether. You know, if light is a wave moving, what's it moving in? What's waving? You know, they came up with the idea of ether as the stuff of vacuums of just space. And of course, we quickly outgrew that silly notion. And now we know that it's actually the Fermi suit. The fact is that when you get into quantum field theory, you start discovering things like the background of Fermi soup, and it turns out that ether may not have been such a stupid idea after all. But time of Einstein, we're still trying to figure out why. You know, what's wrong? Why won't light? Why can't we measure the difference in the speed of light? Why doesn't it behave the way everything else does according to relativity? Because remember, relativity wasn't a new idea with Einstein. It went all the way back to Galileo. Galilean relativity. The speed of objects being, varying depending on the reference frame of the observer. Well, Einstein just said, okay, so the speed of light is invariant. It doesn't change. It's a constant. And that's why in his famous equation, it's designated with the letter C for constant. Turns out that whenever you make that assumption, things get really weird really quick. And that's what we're going to look at. Is how some of these things change. But before we do, I want to try and try and impress something upon you. Because I really believe this is important in order for you to better understand the in context, all of the stuff that you're learning. Not only this, but other things as well. People think of relativity and they think of the Lorentz transforms, and time dilation and speed of light, slow, time stopping, time travel. Trains get shorter, and we'll look at that how if you've got a train going fast enough, you can fit a 100-foot long train inside a 50-foot long tunnel. How does that happen? Well, if you go fast enough, it does. But all of these complexities that grab the imagination are not the point of relativity. The point of relativity is, of all science, is not what changes. The point is what stays the same, what doesn't change. Think of it like this. You got some guy sitting here in his inertial reference frame. And this is a very grossly oversimplified analogy, but I think it'll make the point. Here's his reference frame, X and Y. And here he sits. And he says, I want to go to this point here. Call it P. He says, well, that's easy to do. I'll just go I'll go east 6 marks, and then I'll turn north 5 marks. So this guy here, A, says if I go east 6 and then north 5, you'll go from here to point P. Well, standing here next to him is this other observer, B. Only B uses a different coordinate system. For him, this is positive X, and this is positive Y. This is minus X, and this is minus Y. And he says, okay, east 6, north 5. He winds up out here somewhere and says, what are you talking about? The P is nowhere to be found out here. And he finds P and he says, oh, wait, look. You only go east 2, and then you go north 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now, I did not do a calibrated example here, but you see how he would get a different set of directions. He would get east 2, north 10. Well, this is just the way things change because of your frame of reference, how things change relative to your perspective. But what doesn't change? What stays the same regardless? The distance from point A or point B to P is always going to be the square root of the sum of the squares of the sides. Pythagorean's theorem. This will stay the same regardless of their frame of reference. Okay, and if they both use the same calibrated units of measure, then they can both look at it and say, yes, in mine it's 2 and 10, in yours it's 5 and 6, but if we take the square of the sum of the squares, then we find out that in fact we both have the same distance measured. I really should work that out with some actual numbers where you could do the math and it would make the point better, but I think the point is made nonetheless. This is what matters. This doesn't change. In special relativity, C is what matters. (299 times 10 to the 8 meters per second. Is that right? Or is it 2.99? I don't care. I need the point in there?
Yeah, they're the same as 3 points.
Okay, 2.99 times 10 to the 8 meters per second. That doesn't change, ever. No matter what else has to change in order to accommodate this fact, this doesn't change. Maybe you have to go right 3 and north 2, or left 6 and south 8, but you're going to end up at the same point. That is what doesn't change. But things that do start to change, when you get very near the speed of light, or even close to the speed of light, can start changing in some very surprising ways. Do any of you appreciate contextually, from a historic perspective, the significance of this kind of scientific advancement? Think back. We're looking at Einstein and how he thought about the constancy of the speed of light, but what did he do? What happened? And who was it? Was it Galileo? No, it was Newton who said, "If I have seen farther than other men, it's because I've stood on the shoulders of giants." Back at the beginning of the semester, I pointed out to you, Galileo was the first of his kind. He was the first person to introduce the scientific method, where prior to Galileo, there was no science. It was philosophy. It was philosophers thinking about things and, imagining things without empirical confirmation. And just trying to make sense out of what they could observe based on nothing but their own understanding. That's great. And I'm not diminishing the value of that. To the contrary, what I'm about to do is point out the value of that ability. But I also want you to bear in mind that that ability, as valuable and as powerful as it can be, if left unchecked, will give you things like the geocentric model of the universe and 2 realms of terrestrial realm and celestial realm with 2 separate laws of physics and 2 different laws of how things move. In the terrestrial realm, the philosophers figured that in the terrestrial realm, the natural state of motion was to be at rest. But in the celestial realm, the natural state of motion was for things to move in perfect circles. And it made sense. It's exactly what they observed. Everything in their universe revolved around them. But everything around them came to rest. Once you let it go, once you stop pushing it, it stopped. Galileo took that thought experiment, combined it with actual experiment, and set in motion, centuries of scientific advancement. He had the ability. He did that thought experiment. He took something and he said, "Well, wait a minute. This is the way it looks to me, but what if it's actually a little bit different?" And he looked at it from a different perspective. He said, what if the only reason things come to a stop is because something is stopping them? What if we eliminated that something, that force that's acting to stop them? Then what would their natural state of motion be? Everybody knows his most famous experiment, the most famous experiment in the history of science, the first experiment in the history of science. He dropped two balls off of the Leaning Tower of Pisa. They both hit the ground at the same time, even though one was dramatically heavier than the other, proving that all matter undergoes the same acceleration. The force may vary. Force varies with the mass, but the acceleration is the same. He looked beyond the friction of something rolling across the table and said, and this was basically his thought experiment. He said, if you take a ball in a track, and you set it here, and you drop it, it will roll down, and it will roll back up the other side, but then it will get up that high and go no higher. Stop. So eventually it'll settle in the bottom. So is that the farthest, the maximum distance it could roll? Could it not roll any further than that? So he made the track longer. And sure enough, the ball rolled back to that same height, but it moved a much further distance. And no matter how long he made the track, it just kept rolling further and further and further back to that same height. And he then extrapolated, well, what if the natural state of motion is not to stop, but to continue moving in a straight line until something else stops it? That had never occurred to anyone before. And he coupled that kind of insight, that kind of ability to extrapolate to a higher perspective with just the common sense approach of empirical confirmation, empirical measurement, and he changed the world. Newton, next guy who came along, did the same thing. Everybody knows what did Newton do. Okay, well, he invented calculus about the same time Leibniz did. What else did he do? Why was Newton the most famous? And partly because he was also the president of the Royal Academy of Sciences. And Leibniz was this little German scientist working out in the hinterland somewhere. But it's also because Newton took all of these different laws of motion, the terrestrial realm and the celestial realm with their separate laws of motion and physics governing them. And he said, what if they're not the same? What if they're not different? What if they're the same? And how did he do that? He looked and he did a thought experiment when an apple hit him on the head. And we've gone through it in the class, where he envisioned, well, we went through it in Physics 1, where he envisioned, what if you threw the apple? It's still going to fall to the ground, but it's going to travel further before it does. But what if you got on a really tall mountaintop and you kept throwing it faster and faster and faster? Eventually, it would keep falling, but it would fall at the same rate that the earth falls away from underneath it, and it would come all the way back around and hit you in the back of the head. He envisioned that as a thought experiment, and then went on to empirically confirm his hypothesis with real experiments. He was not met. He was not, the people at the time, they were ensconced in this doctrine that there were two realms with two separate laws of motion, and this notion of universal gravitation affecting everything in one set of laws of physics that governs all motion everywhere. That was out there for them. That was anathema to their doctrine. And Newton actually cited Kepler, and Kepler Kepler's laws of motion and showed that that's part of how he got it, he finally came to get it accepted, was he showed that his laws of motion would explain everything that Kepler had observed and documented. And that was a big part of what got his work accepted. Because he was able to do that thought experiment to extrapolate, what if, okay, yes, I know I can only throw this baseball, well, you or I probably 50 or 60 miles an hour. Major league pitcher, maybe 100 miles an hour. But no one's going to throw a baseball 25,000 miles an hour. But he could still imagine, what if you could? What would happen? That's what Einstein did. He said, well, what if this is true? What if the speed of light simply is a universal constant, and it will always measure the same in every reference frame, regardless of the speed, the relative motion of the source, or the receiver, or the observer? Well, let's do one of those thought experiments right now. Simultaneity. Am I pronouncing that right? Yeah, simultaneity. I'm write it out. Simultaneity. In other words, two things happen simultaneously at the same time. What does that mean? It means just that if two things happen at exactly the same moment in time, then they happen simultaneously. But what if they're moving? What if one or the other is moving in a frame that's moving relative to the other? So let's, the fact is we know that the speed of light is finite. If something happens a long way away, it may take a considerable amount of time for the light reflecting off of that event to reach you, the observer. Okay? So, let's say you are the observer. And you are here at some great distance away from 2 points, both of which are exactly the same length. You're right dead nuts in the middle. Now, if an event happens here at time t equals t0, and an event happens here at the same exact time, t0, and it takes the light traveling from this event, this distance, t, which would be, we'll call that delta t, so that it's distance divided by the speed of light, or the speed of light divided by distance. And the light from this event at the same time has to travel exactly the same distance. It will take it exactly the same amount of time to travel there. And so you as the observer sitting in the middle would be able to observe that both events happen at exactly the same moment. Now, it would take you some doing to calculate how far away they were, how fast was light moving to get there. So it would take, you'd have to do some math to figure out exactly when in your time frame those two events happened at the same moment. But you could do it. And because you observed both of them from exactly the same distance away, you could say that, yes, they both happened at exactly the same moment. Now, how how does this change if if two observers are observing the same events, but one is moving relative to the other? So we can put them in spaceships or rockets or whatever, but it's convenient to put them in trains. So we'll put them in trains and just say these are extremely fast trains. So here's one rail line. Here's another rail line. Here's a train car. Here's a train car. Rail line. Rail line. And for the sake of our thought experiment, we're going to say these are some pretty long train cars. Now, these two cars are moving relative to each other with a relative velocity between them of v. Now that means observer 1 in this car says that observer 2 is moving that direction at v, at a velocity v. Observer 2 says, no, observer 1 is in that car moving in the opposite direction at a velocity of v. We could, we could take a third position on the ground next to the trains and decide, based on our frame of reference, which train is moving with what velocity relative to us. But at the end of the day, there is no preferred frame of reference. So it's not possible to say, yes, this one is stationary and this one is moving. All we know is that between the two of them, they're moving relative to each other at velocity v, and we can consider whichever one we want to be stationary, and we're then in that inertial reference frame. Now, this is on page 749. Turn to actually page 750 now if you really want to look at it. Assume that at this moment, at the exact moment that they are perfectly parallel to each other, at this point, x, lightning strikes both ends of this train, of these trains at the same time. Now, it marks the trains here and here and here and here, exactly the same distance apart in both frames. Now, the light traveling from that lightning strike travels to observer 2, and they both reach him because they both happened at exactly the same moment. They both reach him at exactly the same time, and observer 2 observes that the lightning struck both ends of this cart at exactly the same moment. They happened simultaneously. They were simultaneous events. But this guy is moving at velocity v. So, let me get a different color. At some later point here, this observer has moved down here. His train is now here. The light from this strike has already passed him, and the light from this strike has not yet made it to him, because he's moving in that direction. The light is moving at the same speed, the same velocity in all cases. But because he's moving, it takes longer for that light to travel this distance. less time for this light to travel that distance. That means for this observer in this car, this lightning strike hit significantly before this one did. And they did not happen simultaneously at all. Now, everybody up to speed with me so far? Okay, now it's time to twist your noggins. Which one's right? Did the events happen simultaneously or not?
Yes, because the one in the car that got struck by lightning, he's in the middle, so he is seen exactly at what time.
But only because we chose to observe from his frame of reference. If we were in this frame of reference, then this lightning strike would have hit first, and then later this lightning strike would have hit. But because he was moving fast in this direction, he would have moved to the point where the two light paths intersected at the moment they intersected. And he would have observed them as simultaneous, whereas we actually saw them happen several seconds apart.
So it's all just based on your reference.
It is all based on your reference. But this is a really serious fundamental question. Is it even hypothetically possible for two things to happen simultaneously? Actually happen simultaneously. What this calls into question is, how does time progress? Okay, this is the issue of simultaneity. How does time actually progress forward? Everybody agrees that time moves forward in one direction only. It's relentless, monotonic forward progression. Well, at least it is monotonic and forward only, as best we understand it now. But if the speed of light is truly a universal constant in every frame of reference that does not change, then whether or not two events happen at the same time depends entirely on your frame of reference. Time would then have to move differently in your frame of reference based on how fast you're moving, or based on something. You would have to perceive time differently based on your frame of reference. And that means time itself would actually have to progress differently. Here's another example. Got time? Yeah, we've got time to look into this. Time dilation. All right, I want to do this one carefully because this is going to introduce something pretty significant. So we got a fella moving. We got a fella in a box. All right, and he wants to measure the speed of light. So he sets up a transmitter here, and a receiver here, and a reflector over here, on the opposite side of his room. And he emits a pulse of light, boom, boom, boom. And that pulse of light travels across the room. We'll call this distance D. And then it reflects back over to this receiver. And so this beam of light travels 2D. That's how far it's going in a time delta t. And that would then have to equal the speed of light, c. Now, let's assume that this guy is actually moving to the right with a velocity of v. And you're an observer watching him from the ground. Now that means when he fires this beam of light, he's actually over here. And here's his little transmitter and receiver. And here's his mirror. And he fires that beam of light. Boom, boom. Well, as it is traveling across the room, he is moving forward until he gets here. Just as that pulse of light hits the mirror and reflects off and starts coming back the other direction towards the receiver, which by the time it does, he's now then traveled over here. Here's his transmitter, here's his receiver, here's his mirror, and the light is just now reaching his receiver. Now this is still V. But look at how far that beam of light actually had to travel in your reference frame. Because that beam of light had to travel a much further distance, but it's moving at the same speed, c. I was going to say it had to move a much greater distance, m times d, as opposed to 2 times d. We'll call this delta t prime, meaning that it's relative to this frame. But that is still equal to the same speed. In other words, the ratio of this distance to this delta t is equal to the ratio of this distance divided by this much larger delta t. That means because he was moving relative to you at a very high rate of speed, from your perspective, that his time had to be moving much, much slower. They work through the derivation of the equations here in the book. They're not very difficult to follow if you look at them. You can work your way through them. They end up with this. V over c to V over c squared. Does anybody recognize that equation? Here, this is, let me change this so it matches what I've written here. And we'll just call this delta t. This term right here, in fact, is so significant in relativity that it's given its own name. The Greek letter gamma is defined as 1 minus velocity squared divided by the speed of light squared. Now, what happens if if your velocity actually achieves the speed of light? What if you actually got to the speed of light?
Damn, it all cancels here.
This would become 1, and it would become, gamma would become the square root of 0, or 0. T prime would then become that divided by 0, which would become infinity.
Yeah.
Time would basically stop. Okay, actually, you might recognize c squared from a famous equation. This does have to do with the amount of energy it takes to get to that spot, to that point where time would stop completely. But since it never does quite get since you can't actually get to the speed of light, or as long as you can't actually get to the speed of light, this will always be slightly positive. With time dilation, the faster you go, the slower time moves. Well, relative to other people, relative to the observer watching. Time would still be moving at the normal pace in your frame of reference. You're in this frame of reference, delta T naught is delta T naught. But the people observing you on the ground, time in your frame of reference is going much, 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 much slower. So, relative to people on Earth, you want to go to Alpha Centauri Proxima, or whatever the name of that nearest star is, it's what, 30 light years away. That means if you could actually get to the speed of light to see, then it would take you, relative to us, 30 years to get there. If you're moving at the speed of light, it takes you 30 years to go 30 light years. But how fast would you be going? How fast would it seem to you that you moved? Because remember, to the observer on the Earth who watches you for 30 years go to get there, time in your frame of reference is going to slow down dramatically. So, how long do you want it to take? Do you want to be able to make the trip in an hour? Well, set delta T prime to an hour. Set delta T naught, set delta T naught to an hour. Set delta T prime. Point is, you can do the equation, you can do the math, and figure out that if you speed up to this velocity, it'll take you an hour to get there. That's what it'll seem like to you. Now, the people observing you, that took you 30 years. What if you don't want to wait an hour to get there? What if you want to wait until you want to get there in a minute? Just redo the math. You'll have to get to a much higher velocity, but it's still going to be less than c. In fact, as long as you can get arbitrarily close to the speed of light, then you can make that trip in your frame of reference as arbitrarily quickly as you want. You could do the math and figure out what velocity you would need to achieve in order to make the trip in a microsecond. Okay? It will take lots more energy every time you do it. The faster you go, the more energy, exponentially more energy it's going to take. But if you can get arbitrarily close to the speed of light, then you can make the trip as arbitrarily short as you want it to be. There is there's a video I want to bring. I want to get it next time for us to watch. It's on a little YouTube channel called Mineral Physics. This all seems like it's pretty esoteric stuff, right? Kind of, yeah, but how does this okay, so it makes sense, you can think it through and make it a thought experiment, but does it really happen? As it turns out, so far, everything about Einstein's theories of relativity that we have been able to test empirically, it's all proven true. It's all confirmed. So far, nothing predicted by his theories of relativity, special or general, has been refuted, has been empirically refuted. Now, there's still some things we haven't been able to test. Any one of them might fail. But this time dilation thing, it actually does work. It actually does happen, and it has been empirically confirmed. And this video shows it does an excellent job of showing you exactly how it has been confirmed with muon decay. I don't know if y'all have ever heard of muons, however you want to pronounce it. So the subatomic particle, it's called a muon. And it's pronounced muon or muon, depending on who you ask. But it's a subatomic particle. Has an incredibly short lifespan. Okay? But it turns out that bunches and bunches of them are generated in our upper atmosphere with solar radiation striking the upper atmosphere. And those muons, given their incredibly short lifetime, would not live long enough. They wouldn't survive long enough to travel more than a few hundred feet down into our atmosphere. In fact, significant numbers of them actually survive long enough to make it all the way down to the surface of the Earth, and we can measure them. Except that's not possible, because they can't survive that long. We've built them, we've made them, we've produced them in the lab and measured their lifespan. Well, turns out that if you do the math, and you take into account the velocity of these muons when they're generated in the upper atmosphere, turns out that they would in fact live long enough to make it just past the surface of the Earth, and they do. It's really cool. I'll try to remember to bring my laptop next time and pull up the video and watch it. I would recommend that y'all read through this time dilation chapter. Work it out, get it straight in your mind how it works. In the meantime, we'll look at length contraction next time. And see we'll look at how you can fit a 100-foot long train inside a 50-foot long tunnel. You can just get it fast enough. Any questions?